Hello everyone. This is 1 p.m. Eastern time sharp, so we're starting our colloquium. Today we have presentation about Type 3 burst by Hamish Wright, who is currently a solar physics lecturer at University College London. He undertook his PhD at the University of Glasgow on solar electron beam propagation through the heliosphere. Since then, Hamish has specialized in solar type 3 radio bursts and combining these observations with numerical simulations to diagnose the plasma properties of energetic electrons, thermal electrons, and plasma waves. So please go ahead, you have 45 minutes.
Okay, so thank you, Gregory, for and everyone else for tuning in to listen to about this science. So, as it says in the title, I'm going to be talking today about Type 3 radio bursts and energetic electrons, turbulence, and waves that affect the emission. I'm just going to start with a bunch of some small amount of basics about Type 3 radio bursts for those that are not familiar with it. Talk about some of the observations. And some of the exciting results that we should hopefully be getting with Solar Orbiter and Parker Solar Probe that are coming up. And then I'll talk to you about a study that I've done on Type 3 radio burst fine structure and how we can use that to diagnose plasma properties. I should say as well that a lot of this work was done with my collaborator, Eduard Kontar, as well. So what happens in the sun is we have a large explosion, solar flare happening in the atmosphere of the sun, accelerating electrons out through the solar corona and into the solar wind. And it's these electrons that are responsible for the production of Type 3 radio bursts through the plasma emission process. And the theory was generated a long time ago, back in the 50s. And there's been a couple of recent reviews, including one that I wrote last year on some of the recent imaging spectroscopy that's been done using the sort of new age imaging spectroscopy, like from the VLA and LOFAR and MWA and so on. So one of the most important features about these Type 3 radio bursts is that they change frequency as a function of time, and this is called the drift rate. And the drift rate reflects how the electron beam is moving through plasma with a decreasing background density. And so I've got this little schematic to sort of highlight this. So at the start, the electron beam is close to the sun in the corona where the density is high. And as a function of time, this electron beam expands and travels out into the solar corona and into the solar wind and goes into plasma of decreasing background density. And so consequently, the frequency that the radio emission is being emitted at, which you can see in this Type 3 burst at the bottom panel, decreases as a function of time. So we're able to use the changing frequency to understand where the electron beam is as a function of altitude from the sun. And so this is really important for a lot of the theory that we use to understand the electron beam transport using radio bursts. A lot of the work that I'm going to be showing is using data from the low frequency array. So I thought I'd introduce this for those who don't know about it. LOFAR is an interferometer made up of many stations, which is centered in the Netherlands, but is spread all across Europe. It observes between about 10 and 250 megahertz. And what's really great about it is the sub-second time resolution and the kilohertz frequency resolution that we get. It's got very good spatial resolution, but we don't really need that for observing the sun because we have these extended sources, and it observes in EU daytime. And it's an astrophysical telescope, so much like the VLA, you have to propose time on it. And the Solar Key Science Project for LOFAR, we've been observing time during the PSP perihelions, and we're also making cases for the coordinated Solar Orbiter campaigns as well. So the electron beams that make Type 3 bursts, they can be used to derive the kinetics of the electron beams themselves and also about the background plasma. So the process is the electron beams become unstable and generate Langmuir waves in the background plasma. And it's these Langmuir waves that then interact and produce the radio emission. And because of this, you're able to identify not just, as I said, the kinetic properties of the electron beams, but the coronal structures that the electron beams are traveling along. And this study that I did back in 2017 shows you the electron beam propagating along a large coronal loop that is brightened when you look at the peak flux from all of the type 3 the burst. In actual fact, this one's a U burst, so too because it has a U shape in the dynamic range. And in actual fact, we can see this as a function of time, and we can actually track the electron beam as it propagates along, up and along and around the coronal loop itself. So the imaging spectroscopy that you get from LOFAR and other radio interferometers is a really powerful tool. This study itself also concerned about how it can be quite difficult to generate these U bursts on very small loops due to instability times of the electron beams. But you can have a read if you're interested in that. And although I put this slide in, as many people probably know, we have the recently launched Solar Orbiter and Parker Solar Probe. And why these are really exciting, and I thought I'd mention them, is because we're going to be measuring in situ particles and in situ electromagnetic fields close to the sun, which is great because we finally have a platform to test all of the theories that we have of electron beams traveling from out from the solar corona and in through the solar wind. And we can combine not only the in situ measurements, but also the remote sensing measurements as well from radio and some of from Solar Orbiter, as well as the ground-based observatories like LOFAR, and really sort of probe and kind of try and understand exactly what's happening as these electron beams travel out from the sun. So we can diagnose a lot of properties, but really what questions actually can we answer with these? And so I thought I'd talk about this for a little bit using some previous studies that I've carried out on electron beam transport. So type 3 bursts don't just start at the frequency at the acceleration region, or rather, we don't think they do all of the time. But what exactly governs when an electron beam starts to produce type 3 radio emission has been the subject of a number of studies. What I mean by the starting frequency, if you can see there in green is highlighted what frequency the radio emission actually starts at. And similarly, we have the stopping frequency, which is what frequency the radio emission actually stops at. Why does it stop? So the starting frequency, we believe, is because of the beam instability distance. It takes an electron beam a little period of distance before it actually becomes unstable to producing Langmuir waves. And this is one of the main things that govern it, and it's dependent upon a lot of the electron beam characteristics as well as some of the acceleration region characteristics. And for the stopping frequency, we think it's dependent upon the energy density of the electron beam. And so this decreases as a function of time as the electron beam expands within the solar corona and the solar wind. And it's also dependent on the level of turbulence in the background plasma. But these are just theories. So what we should hopefully be able to do is use these in situ Solar Orbiter and Parker Solar Probe measurements to see if we can confirm these dependencies of the electron beam with the start and stop type 3 frequencies. We can also look at the evolution of electron beams. So it's been observed in the past that if you look at the type 3 burst, from the drift of the type 3 burst, frequency versus time, you can estimate the velocity of the exciter that is producing the type 3 burst. And we found that this exciter speed decreases as a function of distance from the sun. But some recent observations, and I've highlighted some of the plots from it there, have shown that actually, if you simulate this, you can get a velocity increase close to the sun, although it's not really been found using the higher frequency type 3 observations yet, this velocity increase. And so, is this the case? Do we actually see this? Can we find and sort of track this decrease in the velocity of the electron beams with respect to the type 3 burst? And it's largely based on the fact that the electrons are interacting with Langmuir waves at certain velocities. And so we observe Langmuir waves with electrons around about 10 keV or less, about 1 AU. But what we expect is that closer to the sun, the electron beams will be interacting with Langmuir waves at much higher energies. And so when we measure the electrons at, say, 20 keV, 40 keV, we should observe simultaneous Langmuir waves at the same time. So can we use the in situ observations to sort of measure this beam slowdown and relate this to the Langmuir waves that they're producing? The simulations also showed a rather interesting fact that the energy density of the electrons was directly proportional to the peak brightness temperature of the type 3 burst. Now, this is something that we haven't really, we don't really understand as much before this, because it's quite a non-linear process. But this is assuming fundamental emission, that essentially the level of Langmuir waves that's being produced couples with a bath of ion sound waves to produce this fundamental emission. Then it's really the energy density of the electron beam that controls the amount of Langmuir waves, and so the amount of radio emission. And so the plot on the left is the energy density, and then we can make some assumptions in our simulations to find the actual beam energy. So this sort of postulates that the brightness temperature is directly linked to the beam energy density. So is this the case? And so it'll be really great to again use the in situ observations from Solar Orbiter and Parker Solar Probe to confirm this. Although it's quite difficult because it requires multiple spacecraft measurements. We don't know whether we're right in the core of the electron beam cross-section, or we're on the edge of the electron beam cross-section. So it might be quite difficult to again confirm this with just one spacecraft. We'll have to use like maybe 2 spacecraft or 3 spacecraft that are observing in situ the electrons at the same time as the radio emission. We also see a change in the spectral index of the electrons. So we inject them with a power law distribution, and as a function of time, that power law turns into a double power law. A double power law energy distribution is exactly what's observed at the Earth from spacecraft like WIND and so on, and indeed now Solar Orbiter and Parker Solar Probe, or sure, certainly Solar Orbiter study at the moment. And so we found that in the simulations, this double power law comes because the higher energy electrons, there's not enough energy density to interact with the Langmuir waves, but the lower energy electrons, there is enough energy density to interact with the Langmuir waves. And there's an energy loss, which causes this the steepening of the spectrum. And so just taking a still there for the 6 different distances towards the Earth, we found that in actual fact, the ratio of the higher to the lower spectral index depended upon the simulated level of density turbulence in the background plasma. So the higher the density turbulence, the less Langmuir waves were produced, and so the smaller the steepening in the power law. The less, if you don't have as much density turbulence, you get a larger steepening in the power law because more Langmuir waves are generated, and then there's a larger energy loss. So can we again use the measurements of Solar Orbiter and Parker Solar Probe to confirm this wave particle interactions are actually causing the break, and whether or not the amount of density turbulence is affecting the ratio of low to high in the spectral index.
Hamish, can I ask a clarifying question?
Yes, of course.
Sure.
This is Jim Drake. So when you're doing the simulations of this, do you put in a kappa distribution for the electrons? Is it anisotropic or isotropic? And then do you add that on top of a background Maxwellian distribution? Could you give a little bit more information on the
Yeah, that's no problem. I have some slides at the end. I can perhaps actually no, I can just talk about it. So the electron beam is injected into the solar corona. It's injected as a power law distribution with a spatial extent and a temporal extent. And it's injected into a background plasma, which uses the sort of Parker solar wind density model. Okay, and that Parker solar wind density model is well, you approximate it as a Gaussian distribution, so not a kappa distribution, which is something that needs to be slightly modified in the simulations probably. And then we add a level of density turbulence on top of that density model. And we such that the level of density turbulence has a level delta n over n of the fluctuations. And then we don't evolve the background density model as a function of time, because the evolution of this model is a lot slower than the propagation speeds of the electrons actually traveling through it, is the approximation that we take here. And so then the electrons are allowed to travel out from the solar corona and through the wind, interacting with Langmuir waves, producing the Langmuir waves, and so producing the radio emission. Does that answer some of the questions you had?
Yeah, thank you very much.
So in terms of the difference between the kappa distribution and the Maxwellian, there was actually a really interesting study by Lee and Cairns in 2004, I'll go out on a limb, where they estimated the difference between the kappa distribution and the Maxwellian, and you end up having an increase in the Landau damping effectively at the lower phase velocities of the Langmuir waves. So it's something that we bear in mind, but this decrease will be happening at around about a few keV, which is outwidth of the region of interest that we have, certainly for this study at the moment. And so finally, before I continue about LOFAR observations, the level of density turbulence, as I mentioned before, modulates the amount of Langmuir waves that are produced. And so this simulation is showing it's 9 different electron beams propagating through plasma with an increasing level of delta n over n, this level of density fluctuations. And you can see with 0 at the top and about 0.03 at the bottom, the Langmuir waves are significantly modulated as the electron beam propagates along. This is the electric field relating to the level of Langmuir waves. And so again, can we define how the background density turbulence is playing a role with these wave particle interactions, which is the subject of the study that I'm going to talk to you about next. So it moves on to what's called type 3 striae bursts, or some type 3b bursts, as you may have heard. Now, these are essentially type 3 bursts, like I showed before, but as well as this sort of standard backbone of drifting emission as a function of frequency and time, you have this fine structure that you can see here all along the backbone. Okay, now these striae bursts were observed in, well, sort of documented in the 1970s by Delano. And some of the properties are a very short duration and characteristic frequency widths of about delta F over F of 0.1, which is typically independent of frequency. Okay, and so there's been some theories about what is actually causing these striae, but there's a number of properties that are sort of puzzling and led to some competing theories. So one of the main ones is that the drift rate of the individual striae have been found to be about 0.6 megameters per second. And so that's actually, that's like the drift rate. I can't remember the exact value of the drift rate, but this is the speed, sorry, of the exciter when you estimate that speed from the drift rate of the individual striae. So here you can find in the right-hand side an example of one striae from a study, and they've taken the frequency as a function of time, changed frequency to distance using a density model, and that's how they're getting this, or deriving this 0.6 megameters per second. Now, this speed is significantly smaller than the speed of the electron beams, which is around 100 megameters per second. But it's much larger than the coronal sound speed of about 0.2 megameters per second. So one of the questions is, what dictates the striae drift rate? Why are these striae, these sort of small clumps in frequency space, drifting at these rates? And then the other important question that I always ask myself before I do any science is, why do we actually care? I mean, okay, great, so they're drifting at this, who cares, right? Well, it's long been thought, right, from a number of studies, that the background electron density fluctuations can modulate the Langmuir waves and potentially cause this radio fine structure. And I showed you already the simulation where you increase the level of density fluctuations and it increases the level of Langmuir wave modulation. And indeed, people have used this along with the wave refraction of Langmuir waves in the changing background density. And there's a number of studies, there's 4 which are cited here, but there's many more that have actually looked at turbulence and Langmuir wave growth. In actual fact, the Lee and Loy produced synthetic type 3 radio emission as well with respect to the fluctuations. And so, yeah, the Langmuir wave growth is modulated. Well, this is what we think is modulated. And not only that, a recent study by Chen et al. Used the LOFAR observations, which you can see in the left, and they plotted the power spectral density. And they actually found that the power spectral density of the radio emission obeyed this -5/3 power law, which is a similar, well, 1.71 here, which is very similar to the -5/3 power law that's expected from the Kolmogorov density turbulence in the inertial range of, or in the inertial range. And it's also what is actually observed within the solar wind, although the frequencies that LOFAR is observing at is at the solar corona. So this provides an idea that it is indeed a sort of more evidence that it is these density fluctuations that are producing the fine structure. However, nobody has created a robust theoretical model that actually links the level and the spectrum of the density fluctuations to the observed radio spectra, like the actual theory behind this. And indeed, the theory is required if we want to use the type 3 radio emission as a diagnostic, not only of the density turbulence, but also potentially of the electron beam characteristics themselves. And that's where the study that I'm going to go over next highlights and strives to answer this question. So what we did is we analyzed 3 type 3 striae bursts observed by LOFAR. Now, we specifically chose striae bursts that showed quite a lot of fine structure to sort of highlight the results that we had. The 3 dynamic spectrum are shown on the right-hand side with an associated density model. We use the same one we used for the simulations, which is this Parker density model normalized by Mann et al. In 1999. And the top one, the top type 3 striae burst, was actually a subject of a number of other studies, as Kontar, Sharikin, and Chen, and so on. I think there's a few others that studied this event as well. And so doing the standard type 3 diagnostics, what we can do is we can fit a straight line, well, we change frequency into distance via density model again, well, you can see the density model here, and then you fit a straight line through the backbone, and you can estimate the electron beam bulk velocity. And we did this for these 3 bursts, finding bulk velocities of around about 90 to 50 megahertz, respectively. If we then use LOFAR to make observations, images of these, you can see the 3 type 3 bursts on the right, where the white is around about 40 megahertz and the red is around about 30 megahertz. So this is, you can see the decreasing frequencies looking like they're becoming farther from the sun, with the source size getting slightly larger, as we'd expect. I should add that the study that I'm going to be talking about is in Press in Nature Astronomy, and the archive indicator is below. So what we wanted to do is we wanted to characterize the level of density fluctuations that actually occur in these striae bursts. So what we did is between 30 and 40 megahertz, we found the peak flux as a function of frequency, which you can see here with the associated error. And then we've plotted a smoothed function through the peak fluxes. And so we have I as a function of frequency, intensity as a function of frequency is the blue dots, and then delta I, which is the difference between I and the smooth peak flux. And then we use this formula to calculate delta I over I, which we define as the characteristic intensity of the fine frequency structures. And we found levels of about 1 to about 1.4 for the 3 bursts themselves. And we'll use these figures a bit later. But why we wanted to characterize this delta I over I is because we want to see if we can relate this intensity of the fine structure to the intensity of the density turbulence. Now, the motion of Langmuir waves traveling with a group velocity, as the Langmuir waves travel with their group velocity, they are traveling through a medium where the density changes. And so, as we know with any waves, like for example light in the air going into water, you get a shift delta V in the phase velocity when the light refracts off of any density gradient, or in this case density fluctuations with intensity delta N over N. And it's this shift in the phase velocity of the Langmuir waves due to refraction that is actually causing the modulation. And we showed with a derivation that I'm not going to go through this presentation, but it's contained in the end of the paper, that we can relate the intensity delta N over N of the background density turbulence to the intensity of the radio fine structure using this relation here. Okay, where the variables that it depends upon are the thermal velocity and the electron beam velocity. And you can actually use this formula for the group velocity, and you can see that it's also essentially depends upon the group velocity divided by the electron beam velocity. Okay, but this used many assumptions to actually get this model, as a lot of analytical theory does. So how robust actually? Oh,
and what is the electron beam velocity?
So the electron beam velocity is the velocity, the sort of bulk electron beam velocity that you can estimate from the backbone of the type 3 emission. So in these cases, it was around, they say 90 megameters, 50 megameters. So this is what I mean by the electron beam velocity. Although the electron beam in itself is actually made up of many, many velocities. You get this sort of what's called a beam plasma distribution as the electrons interact with the Langmuir waves, and the electrons typically move together with a roughly constant speed. Well, yeah, roughly constant over short distances. And so what we then did is we want to prove this, or to rather to more robust see if this formula actually works using simulations that take into account more complicated physics, essentially. So what we did is we ran electron beam simulations, and first to simply show how the Langmuir waves are modulated by the density turbulence, we created a synthetic corona, or rather just a corona which had a constant background density. So not really a solar corona, but it was around densities relating to about 30 megahertz. And then we put in one sinusoidal fluctuation through this. And the corresponding plots on the right-hand side show the Langmuir wave energy density created by an electron beam moving through this plasma that has this single sinusoidal fluctuation. And you can see that the intensity of the Langmuir waves is modulated at the same wave, the same wavelength as the fluctuations that we put in. And not only that, as we change the value of A in the sinusoid here, when we increase it or decrease it, we increase the amount of modulation of the Langmuir waves. So the Langmuir waves are very much dependent on the property of the density turbulence that is in the background plasma. And similarly, the bottom plot shows you this was without group velocity. So we set the group velocity to 0, and when we increase the group velocity, we get a slight displacement of the Langmuir waves. Now, why is that important? Well, here is the power spectral density as a function of wave number for these. So the top plot really shows you that the amplitude changes the amount of fluctuations, the amplitude of the sinusoid. But the bottom plot here shows you that with a group velocity of 0, you get a lot of power density spectra at the small length scales, or the large wave numbers. But when you switch on the group velocity, the fine structure at the small scales decreases significantly. And this is because the Langmuir waves are sort of smeared out in space due to moving as a function of distance. So the idea of these, where these are sort of toy simulations, is to really highlight and show you that the Langmuir waves are being modulated based upon the density turbulence, and that their properties depend upon the properties of the density turbulence. So we now move to type 3 simulations with a much more realistic background density turbulence. And so this is, again, electron beams being injected in the solar corona and allowing to propagate out through becoming unstable to the Langmuir waves. And in the top simulation is where we have 1 megakelvin plasma. And we can see that these striae bursts, we create a striae burst sort of naturally, just because of the density turbulence that we've inputted into the simulations. And they're quite similar to the observations, although actually the temporal duration is a bit too long. And I'm glad Jim Drake asked about the kappa distribution before, because we actually think that this increase in the duration is because we're not simulating a kappa distribution. Now, the middle simulation is where you have 10 megakelvin plasma, and we found that the striae are too fat in frequency. They are actually a bit shorter, but they're too fat, and so their properties just don't work. They don't look like the striae that we see from the LOFAR observations. And finally, the bottom panel, you have striae. This was produced with a simulation with no group velocity. And so you can see that the fine structure, well, there's a lot more fine structure, but we see actually too much fine structure. And the type 3 burst is no longer representative of the observed striae burst that we see, and also goes on for far too long as well. So the group velocity is playing a significant role. So why have I been laboring the group velocity all this time? Because clearly there is group velocity, so why are we bothering with it? Well, what we find is that when we take the simulated striae burst and we fit a straight line to estimate the exciter speed of the individual striae, we find that they are moving at the Langmuir wave group velocity. And so what's actually causing this striae drift rate is because the Langmuir waves are being generated at a region in space that's very favorable to producing Langmuir waves, and then this large clump of Langmuir waves is then propagating through space at the group velocity, causing this drift rate in the striae. And we can see from a an observed type 3 striae that the velocities are very similar indeed.
Can I ask
So-
another question about that point you just made? If the striae are drifting at the group velocity, does that mean that these waves are actually modulating the local density and the whole thing is moving together in a self-consistent way?
No, so we don't think that certainly we're not simulating that the Langmuir wave motion is causing any significant modulation in the background density itself. It's the Langmuir waves are essentially moving through some background density structure, so to speak.
Do the Langmuir waves propagate in both directions? In which case, why wouldn't you have drifting going in both directions?
So we do actually see striae, so with positive and negative drift rates, but we see much more with these negative drift rates that we see here. So yes, the Langmuir waves do propagate in both directions. In fact, Langmuir waves back propagating, or sort of scattered Langmuir waves, are the cause of second harmonic radio emission. The Langmuir waves couple with almost oppositely directed Langmuir waves and produce radio emission at twice the plasma frequency. But we expect that because the background plasma is decreasing, that sort of the large scale gradient of the solar corona and indeed the solar wind is a decreasing plasma density gradient that we observe way more with a negative density gradient than with a positive density gradient. And this is what we find indeed when we average many striae of an observed type 3 radio burst. The mean drift rate results in a negative drift rate, giving a sort of positive velocity. Okay, so what we can then use is, if we know this, we have then two formulas. We have the standard formula on the left, which is what people use to calculate the electron beam bulk velocity, where you have the backbone drift rate. This is just a constant, and this is the density gradient. And now we have the striae df over dt, the striae drift rate, relating to, again, this constant, the density gradient, and we now know that this is the Langmuir wave group velocity, okay? And we know that this is related to the thermal velocity squared over the beam velocity, okay? And so we can use these two formulas. If we approximate the background density model, then we can estimate the beam velocity from the type 3 bursts here and the drift rate. And then if we know the drift rate of the striae, we can, this V beam and V beam are the same thing. Apologies for the typo here. Then we can use this derived V beam here and estimate the thermal velocity of the solar corona, and so to estimate the temperature of the solar corona. And we used the average striae velocities of about 0.6 megameters per second that was derived for that first type 3 striae burst from Sharikin 2018, and with the beam velocity of 88 megameters per second gives a thermal velocity of about 4 megameters per second, which is about 1.1 megakelvin. Which is very useful because we don't really have any other ways to estimate the temperature of the solar corona at heights of 1.5 solar radii, which is what we can use LOFAR for. This is slightly sensitive. If you remember, I made an estimation of the density model, but taking a different density model, sort of varying the density model to see how far this would go, we could get it to about 1.4, I think it was, megakelvin. So there's not a huge difference in the temperatures that you're getting using the different density models that people assume. But it is one assumption that you have to make. The simulated striae intensity was very similar, as you can see from this plot, to what you saw for the observed intensity, and we're using the same formula. estimated the delta I over I, all from the simulations. And we found that there was an increase in the fine structure when the background density turbulence was increases, as we'd expected from the formula that we derived way back at the start. And indeed, this is the formula on this slide in the bottom. And so if we take a whole bunch of simulations and we vary the value of delta n over n that is put into the simulations, and we estimate delta I over I from the simulated type 3 bursts, we get all of these points here. And you can see that there is this sort of relation between delta n over n and delta I over I from the different simulations. The different colors are relating to initial beam densities that are changing, and the higher the beam density, the higher the electron beam bulk velocity, which is why you get this sort of range here. Now, the black-green triangle is the simulation that we showed where we found estimated delta I over I, and then found using the estimated value for the thermal velocity and the beam velocity, we estimated delta n over n, and we put it on this plot as well. And then we fit using this formula, sort of a dashed line that you can see goes through the simulations in a very nice way, sort of showing you and sort of highlighting this analytical relation between delta n over n and delta I over I. Incidentally, the level of density fluctuations that we got was about 0.3%, which agrees with the level of density fluctuations that people have estimated from a number of other different methods within the solar corona. Okay.
5 minutes, Hamish.
Yep, I'm nearly finished. Don't worry. 2 more slides. And so, so what else can we do? So this, I should point out that it means that we can actually use the level of density fluctuations in the Striae-Verse to estimate the magnitude of the density turbulence remotely in the solar corona, which is incredibly useful for trying to understand the properties of the solar corona remotely. But not just that. If you remember, there had been a study that looked at the power density spectra as a function of wave number. And so we did the same thing with the 3 bursts. And we found again, indeed, that there is this sort of 5/3 power density spectrum at wave numbers below about 1 in 2 pi over megameters. So you can see here that there is, again, this direct relation between or this estimation between the density turbulence power spectrum and what we see in the radio emission. And the simulated power density spectra below, where the blue one is the one that we had at 1 megakelvin. And again, you can see this, the dashed line showing you this sort of -5/3 power spectrum. And what we also see is this sort of decrease in the power density spectra at the higher wave numbers. And if you remember, I showed you before that the Langmuir wave group velocity is causing this blurring of the spectrum at the fine scales. And so this is exactly what we expect. It's what we see in the simulations. It's what you don't see when you turn off the Langmuir wave group velocity, which is the green curve. And so we're really seeing not only the sort of 5/3, but this reduction in the power, which means that we're hypothesizing that the power density spectrum of the type 3 bursts are giving you an indication remotely of the power density spectrum of the density turbulence within the solar corona, which hasn't really been seen before. Okay, and so with my time's nearly up, I'll come to my summary, which is that the advent of Solar Orbiter and Parker Solar Probe, we can test numerous electron beam propagation theories about the energy distribution, their association with the type 3 radio emission, and how their propagation and their interaction between the background density turbulence produces the radio emission. I also showed that the radio fine structure intensity provides a density diagnostic, sorry, of the spectrum and the intensity of the background density turbulence via the formula we found. And we inferred levels of about 0.1 to 0.3. I should also highlight, actually, before I finish, that this is the density turbulence parallel to the magnetic field, and so not perpendicular to the magnetic field. And we expect that the density perpendicular to the magnetic field, the density turbulence might be slightly larger in magnitude. The fine structure also is allows us to estimate the plasma temperature, which we estimate about 1.1 megakelvin at heights around altitudes around 0.8 solar radii. And then we're also looking forward to the enhanced resolution of orbiter and probe, because they also see the radio fine structure at lower frequencies. They are observing striae with the higher resolutions, and indeed, I think there is a Parker Solar Probe study already showing this, and so this should be able to help us infer the radial evolution of density turbulence close to the sun, where we can't measure it remotely. So I'll finish there. Thank you.
Okay, thanks, Hamish. Very interesting talk. So we are open to a discussion, comments, questions. Most efficient way to raise your hand, and you will be put to the top of the participant list. And do we have any question at this point or comment?
Yeah, Hamish, this is Dale Gary. I had a quick question about your animation at the beginning where you were showing the beam propagation and expanding in this kind of a cone structure.
Oh, yeah.
Does that include any, back reaction of the electrons on the Langmuir waves and the Langmuir waves on the electrons?
So do you mean this one here?
No, your cartoon that earlier than this.
Which one? Sorry.
Earlier than this, where you had
This one.
Yeah.
So this here is just showing you, well, this type 3 burst has been observed by wind waves. So it's not really, wind waves didn't see any of these fine structures that you actually see, or rather we didn't see discrete striae. There may still be fine structure within there, but this sort of cartoon isn't really discussing the fine structure, so to speak, more just the bulk electron beam moving out.
No, I'm just that's what I'm trying to get at, though. Is the beam really covering this much territory in the corona at one time?
Ah, you mean the size of the beam at the top?
Yeah.
So almost certainly, the beam is expanding as the magnetic field expands. So the cross section of the magnetic flux rope that the electron beam is propagating along is getting larger and larger as the electrons are traveling out from the sun. And so not only is the beam expanding in the cross section there, it's also highly likely that you're getting some kind of cross-field diffusion or something like that that's allowing the electrons to expand even farther. And the evidence for this is that we observe electrons at spacecraft around 1 AU, which are much farther apart than we would normally expect. So quite large sort of angles from where the acceleration region we can localize on the sun.
Yeah, just try one more time. I'm talking about the length of the beam.
Ah, the length of the beam.
Yeah,
Yes.
is this just a straight velocity? You know, the electron should slow down, as you mentioned, because the waves are reacting.
Yeah, so this is what we expect. This is it's just velocity dispersion. It's just the fast electrons outpacing the slower electrons. And so
that should destroy the beam if that's the case. So
it will, that is one of the reasons why the beam will eventually decrease in energy density, yes. So that and the cross-section expansion, basically these two are going to cause the electron beam to decrease in energy density. But this is the study that I showed, the 2018 simulation study that I cited, actually we looked at this and we really found that the length of the electron beam increases as a function of time or a function of distance from the sun.
Yes, hi, Hamish. This is Kostas Alexandrakis. Although my name does not appear in the screen, it's me, I can assure you. I
Okay.
have a question concerning the turbulence, the level of the turbulence. Is the level of the turbulence you get from Straya consistent with what you get from scattering? Or with what is
Yes.
required for scattering?
Yes, so there was a study by Edward, I think it's the one in 2019, or there was certainly a study by Peijing Zhang as well, and they've used the properties of the scattering. So this is for those that are not too familiar, this is the radio emission being scattered off of density fluctuations as it moves from the source to where we observe it at, typically at the Earth. And they use the properties of the scattering and the radio emission to estimate the value of delta n over n, the level of density fluctuations. And indeed, we find very similar results of around 0.3, 0.1%, these magnitudes for the intensity.
That's very encouraging. By the way, it was a very nice talk.
Oh,
I
thank you.
enjoyed it. And speaking about type 3s, some years ago, we had found a case of a tiny little flare, eruption, I would transient brightening, I would say, that produced an interplanetary type 3 going not as far as the Earth, but quite far from the Sun.
Mm-hmm.
And this had happened. I mean, the location of the brightening was near the border of a coronal hole, so probably the electrons found an easy way out to reach interplanetary space.
Yeah, I think studies that highlight as well that you can get these accelerated electrons not just from big flares like many people think, but also, for example, like you said, so there may be some interchange reconnection that occurred beside a coronal hole.
Yeah, of course, it was during a time that there was practically no activity. So this particular event stood out quite clearly on top of the background. I will put in a link in the chat channel for if anyone is interested in that. Thank you.
Okay, Jim Drake, please.
Hi, very good talk.
Hi there.
So my question is relates to how we reach closure, going from models where we're doing electron acceleration in the flare itself, and asking how does those energetic electrons then propagate out to drive these various instabilities. So for example, if we know what the distribution of energetic electrons are, including the hot thermals as well as the power law tail, if I take a expanding field line and then allow those electrons to expand out along the field line and through a background plasma, will I be able to produce the distribution functions that you need to drive this Langmuir turbulence?
So most likely, yes. I mean, the distribution functions are just simply a positive gradient in velocity space is what you need to drive this instability. And so this naturally occurs from velocity dispersion. So just by injecting a power law of electrons, power law in energy space, with some finite size in space, and over a finite time period, then yes, you almost certainly generate the instability. Now the amount of electrons has to be enough. The energy density of the electrons has to be high enough that you're able to produce Langmuir waves above the thermal level. And so there's a difference there. And also the level of turbulence can't be too high as well. But in general, yes, you tend to produce type 3 radio emission.
So do you think then, so for example, in our simulations now, Harry Arnold just came out with a paper in PRL on this. We find that the energetic component of the spectrum is of order unity. In other words, most of the energy is actually contained in the power law tail, the non-thermal electrons. So
Okay.
it seems as if there must be enough energy density there, but I'm trying to figure out what we have to do to reach closure on this. So I don't know, maybe we can have some email back and forth about this, but it looks to me like we're sort of in a position now where we should be able to reach closure on the source of these energetic particles.
Yeah, I mean that certainly. The type 3 noise storms are a very good sort of example of this continuous particle acceleration producing a large amount of electron beams over hours or days. And was sort of an example of the radio signatures of prolonged particle acceleration as well. It remains to be seen about acceleration sort of further down in sort of small closed loops as to whether the electron beam can have enough instability to produce the Langmuir waves, and then actually when you go to higher densities as well, you have to contend with collisional damping of the waves themselves. But yeah, certainly happy to chat over email after this.
Okay, Hugh.
Yeah, thanks, Hamish. This is Hugh Hudson. Simple question is, how close is the theory then of type 3 bursts to letting us actually determine the number of electrons in a quantitative way that's required to make one stream?
That's a great question, Hugh. Let me just put up one of the slides that I had here. So if I go back one here, this is where we found that the energy density, or rather the beam energy, was being directly related to the peak type 3 brightness temperature. So these are sort of taking little steps, so to speak, that we can. So I assume what you mean is being able to get the radio emission and diagnose the properties of the electron beam.
How many electrons?
Exactly. How many electrons? What's the spectral index? What's the beam energy? So currently, I mean, this theory, it's sort of yet to be proven with observations, but it would mean that you could potentially, if you had estimations of the spectral index, then perhaps you could use that along with the amount of radio emission to estimate the energy density. Or vice versa, if you had the number of electrons, you might be able to estimate the spectral index or so on. But then there's also the extent of the electron beam that you would then maybe have to estimate from type 3 interferometric observations, taking into account the likes of scattering and so on. So I'd say, in summary, we are taking incremental steps, and hopefully at some point in the not too distant future, we'll be able to use the type 3 radio emission to tell you a lot more about the properties of the electron beam.
Well, just to put this in context, it used to be said by the experts that everything is so nonlinear that you have no idea whatsoever. So now are your constraints down to a factor of 100 or a factor of 10 or a factor of 1,000?
I mean, so the estimations here are based upon from the brightness temperature versus the beam energy. This is for one simulation that we put in. So really need a sort of more of a simulation effort along with some observations to sort of back this up. I'm not going to go out on a limb and say
Okay.
magnitude we are.
Don't want to pin you down too hard here.
But certainly I'd say that yes, you're right. Maybe years ago we would say we're never going to do it, and I'm going to say hopefully we can do it at some point, but it's going to be lots and lots of incremental steps, and we're on that journey now.
Right, thanks.
Very good. Christina, please go ahead.
Hi, Hamish. That was a fantastic talk.
Thanks.
I have what might be a very basic question, but if you could go to your slide that showed the start and stop frequencies of the radioverse. Yeah, that one, exactly. So there are some of these radio bursts that sort of start and stop in fits, right? Sort of like the one near the middle of the panel.
Yeah, shall I move the circles?
Yeah, well, it doesn't actually, yeah, either way. I mean, some of this might be, clearly like the very first one, which is big, is probably due to gaps in, in terms of observations and sensitivities. But I wonder about other ones, say the second one that's sort of big-ish around Nancy. If things sort of come and go, and I don't know if that's a routine observation that you see a type 3 radio burst kind of start and stop, or they're always uniformly consistent throughout the thing. Is that telling you something about the beam per se, or more likely maybe the turbulence that it's in experiencing as it moves out? Because presumably the turbulence is not uniform as it, or a smooth varying kind of thing by definition.
Sure. And indeed, that's the observations indicate turbulence isn't. Turbulence tends to increase as a function of distance from the sun. But the starting frequencies we found are related to the actual altitude of the acceleration region itself. And so the density, the background density in the acceleration region, but also the instability distance that the electron beams have to travel from the acceleration region to where they start producing radio emission. And so these studies here at the bottom, we found that this is heavily dependent on the spectral index of the electron beam itself. So electron beams with a very shallow spectral index, or a hard spectral index, as we know from X-ray observations. So hard spectral indices will go unstable much quicker than soft spectral indices. And this is all related to the fast electrons having to outpace the slow electrons. It's also related to the size of the acceleration region itself as well. But in this case, we may have the type 3 burst that you could see on the left, where you have much higher starting frequencies, is because we have a very hard spectrum. It's producing radio emission very quickly. There's a high energy density and so on. And then this radio emission, it doesn't start till, like, say 80 megahertz or below, is because we have much electron beams with much softer power laws, and so it takes the electron beam a lot longer in distance to become unstable, and so the frequency of the starting frequency is lower.
Yeah, that wasn't actually my question. I understand that the starting, that's okay. You explained it very well, that the starting frequency is dependent on the beams and stuff. I'm talking about, say, like your third set of circles in the middle here, where it looks as if, yeah, so it looks as if the beam, or the burst starts there and then continues and then possibly stops and then continues on in the Nancy, and then maybe fades out and then comes back. And I'm wondering if that's real or an instrumental sensitivity thing, or the beam is changing its spectral shape, or that's what
I think there's two components. One, there can be related to the density turbulence in there, but in this case, the majority is a sensitivity thing. The decameter array is not very sensitive at these lower frequencies, and the wind, also the sensitivity of the wind waves. This doesn't have a uniform color table between all of these different plots, and so the flux here where my cursor is probably larger than the flux below. We think that typically we find that the flux of the radio emission increases as the frequency decreases. But so I think the bulk of this will be sort of plotting issues and or sensitivity of the different instruments.
So you would imagine that once you form a beam and it goes unstable and starts creating these waves, it's going to stay that way, or it'll trickle out, but it won't like disappear and then reform or something like that.
Yeah, I mean, there will be fine structure like the striae, and there might be fine structure and sort of slightly bigger length scales perhaps. But yes, in general, it goes unstable, it propagates away, and then at some point it's going to stop when it runs out of oomph.
Okay, thanks.
Okay, we have one more raised hands, Chile, but we're in the second hour, so please attempt to ask quick questions and give quick answer. Yeah, go ahead.
Speaking of starting frequencies, I remember the work by Antoinette Howell a long time ago, where she found that the highest frequency of type 3s were related with peaks in the hard X-ray flux.
Indeed, and these studies that we've got are not only referencing that study by Rao, but also seeing that correlation between the starting frequency and the hard X-ray spectral index.
And in addition to that, you can have acceleration not only at the low atmosphere, you can have acceleration higher up, secondary shock acceleration in shocks that can produce type 3s starting at lower frequencies.
Yeah, almost certainly. Again, that might be the cause of these ones in this plot, but yeah, it's also that like the origin of herringbone emission that we can see as well.
Well, herringbone and normal type 3s, I suppose. I have seen several of these in plots. I suppose this plot here is from the SECI for the radio monitoring
Yes.
site. And I have seen plots in that site with type 3 starting higher up.
Okay, so let's turn to the last question from Chile.
Okay, thanks. Interesting talk. To clarify, and maybe I missed this. I missed the nature of this. That kind of global transport simulation you did to simulate the burst. So it captured the Lamier instability, it seems to be. And does it capture other instability like Whistler triggered by the electron beams? Just like the nature of the simulation. Sorry.
Yeah, I'd love to also be able to simulate the Whistlers, but no, I have a sort of extended slide here where I can show you sort of the equations. And just quickly, we're looking at the electrons and the generation of Langmuir waves. And there's a number of different physical processes that are inputted into the simulation here. But I'd love to be simulating other plasma waves like Whistlers and so on, but not yet.
Thank you.
Thanks.
Okay, great. Thank you very much. So see you again in third Friday in May. Thank you, Hamish. Yeah.
Thank you very much, everyone.